In the last video, we observed that Newtonian mechanics is incomplete. And in this video, we are going to review the crux of the problem. It turns out that something that we've been using all along, what gets called the Galilean Transformation, will need to be modified. But let's start by reviewing the Galilean Transformation. So this is the kind of exercise that you do when you say, I have a car going north at 50 kilometers an hour and a car going south at 50 kilometers an hour. How fast does the northbound driver say the southbound driver is approaching them? And you would say 100 kilometers an hour. That is a Galilean transformation. But let's just refresh our memory of this from mechanics and also introduce the notation that usually gets used in relativity. So I'm going to schematically represent one of our observers with a coordinate system that they carry with them, and we usually name this observer S. Well, one of the observers S, and then we're going to have, and S is the observer that the narrator in whatever problem says is moving. Of course, when there's more than one observer, each will swear the other one is moving. But whichever one the narrator thinks is stationary, that's the one that we call S. So if someone says, so-and-so is staying by the side of the road, okay, that person is S because that's the one the narrator thinks is stationary. Alrighty. And then the observer that the narrator thinks is moving will get named S prime. And their coordinate system will be X prime and Y prime like that. And we will say that S prime is moving at velocity V with respect to S. So again, here, S prime is the observer that the narrator says is moving. Alrighty. So now let's imagine that some firecracker goes off. Let's say right here. So the two observers will record different values for the position. S will say the firecracker went off at location XYZ. And S prime would say that it happened at X prime, Y prime, Z prime. Now, one thing that we can do without losing our sanity is we can just align our x-axes in the direction of motion, in the direction that S prime is moving and going through S prime's origin like this. So by doing that, then at least both observers in the Galilean transformation will agree on the Y and Z coordinates. However, they will disagree on the X coordinate of the firecracker. This distance here will be X, but here, this is where X equals 0 is going to rest for S prime. So that distance will be X prime. Now, again, to help preserve our sanity a bit, we can assume that when these two origins overlapped, that was when both clocks were set to 0. So at t equals t prime equals 0, our origins overlapped. Now we can loosen all of these assumptions, but it doesn't change anything physically and just makes the math more tedious. So pretty much, unless you've got a really good reason to do otherwise, this is pretty much how everyone rolls with it. So at the time that the firecracker went off, which will be time t, when this happened, and there'll also be t prime, S would say that S prime was located at a distance vt away from them. So looking at the picture here, we can then conclude that x prime is equal to this bigger distance x minus how far away S says S prime is from them at that time t. So the x coordinate measured for the firecracker here will be the x coordinate measured by SS minus this distance here. And as will turn into being a bit of a rule of thumb, you can also convince yourself that if you change the primes, you change the signs. That also works out. But now, let's say instead you were looking at something moving. Like let's say a baseball. So here's our baseball. Now, the observers are going to disagree about how fast the baseball is going. S is going to say the baseball is moving faster. And by convention, since we've already used V for how fast S prime is moving with respect to S, we call the velocity that U measures, or that S measures, U, just because it's the letter before V. So U is the velocity measured by S. And then U prime here, well, S prime in this case is going to say that this ball is going slower. And so we'll say that U prime here is the velocity measured by S prime. Well, how did these relate? Well, the way you measure any velocity is you measure a sequence of x coordinates and divide by the time. So we can just take this and differentiate it. So if we go ahead and differentiate this, this is going to give me dx prime dt equals dx dt minus v, because v is a constant. And this dx prime dt is the speed of our baseball as measured by s prime. This is the speed of our baseball as measured by s, and that's the relative velocity of the frame between the frames. And keep in mind, I shouldn't be saying speed, I should be saying velocity. So everything moving to the right is positive, everything moving to the left is negative. And again, it'll turn out that if you change the primes, you change the signs. All right. Well, is there anything that S and S prime agree on? Well, it turns out, yeah, they agree on the acceleration of the ball. If we differentiate this one more time, here we'll have du prime dt. Here I'll have du dt. And since v is a constant, the derivative of a constant is just 0, so we're done. So the acceleration of the ball as measured by both observers is the same. And by Newton's second law, both observers would conclude that the same forces are being applied on the ball. So if every observer agrees on a value, then we say that that quantity is an invariant. And so the acceleration and the force that an object feels are invariants under the Galilean transformation. All right, well, let's ask ourselves, is there anything else that's an invariant? And it turns out that, yeah, there is. The length of something is an invariant under the Galilean transformation. So if you ask yourself, how do you measure the length of something? You realize, you say, well, that's no big deal. I stick a meter stick up against the thing and I read the number, right? Well, what do? You put 0 to one edge of the thing, and you then looked at the other edge of the thing and you read a number, and you made sure that the meter stick didn't move with respect to it. So really what you were doing was, say if we were measuring the length of this object here, what we've done is we've identified two events. So I'm going to imagine a firecracker exploding here, and I'm going to imagine a firecracker exploding at the other end, and we will record the coordinates of both of these events. And if we're going to be able to measure the length, we need these events to occur at the same time. Keep that thought in the back of your mind for future videos. But so anyway, we need these to happen at the same time. So S would measure that this happened at x1 and x2 at the same time. S prime would have said that it happened at x1 prime and x2 prime. Okay. So how long would S say our stick here is? Well, they would say that the length is x2 minus x1. Okay. Well, let's see how long S prime says it is and see how that compares. S prime would say that the length that they measure would be x2 prime minus x1 prime. But we can go ahead and substitute in the Galilean transformation and say and observe that x2 prime was x2 minus vt. This will be minus x1 minus vt. Well, what do you know? Those minus vt's there cancel, and we are left with just x2 minus x1. So we get that the length as measured by S prime is the same as the length measured by S. So the length of an object is an invariant under the Galilean transformation. And by the way, it will turn out that under the Lorentz transformation, which is going to be the correct transformation to use, they will disagree about this length. But for now, that's what we've got. So maybe let's just do an example real quick about, say, how we could compare the speeds of things. So let's say that S observes two ball, let me back up. Where this kind of thing can be really useful, say, in analyzing collisions. Let's say we have two objects, same mass. And let's say that S says this one is initially moving to the right at 2 meters per second, and this one is initially moving to the left at 4 meters per second. A way that you could do this calculation is you could shift to a frame where one of the objects is seen as stationary. So we can bring in our friend S prime, also moving to the left at -4 meters per second. So then S prime would say that this would be going at 2 minus a -4 is +6 meters per second to them. And this is just plain. Oops. This is just plain stationary. So if they're equal masses, we know that the speed they go apart has to be the speed that they... Sorry, for the example I built, these are not equal masses, but this is an elastic collision. My apologies. So let's say that for some case, when you go ahead and look at this afterwards, you know that the speed of approach has to equal the speed of recession. So let's say you had information that... So you can calculate, say, afterwards that this ball was, in this frame, was going at u1 final prime equals 3 plus 3 meters per second. So it lost speed, and this one gained. And actually I lied. This is equal masses. All right. So then we could go back and figure out how fast S would see it move by adding in 4 meters per second. So, subtracting 4 meters per second. So after the collision, S would say it was bouncing to the left. U1 final would be equal to U1 final prime plus V. So that would be to the left at minus 1 meter per second after we add a negative 4. And we could do the same exercise here, and they would conclude that this was going to the right at 5 meters per second. This would be U2F prime plus V again. So oftentimes it's easier to do these kind of calculations in a frame where one thing is at least initially stationary because it makes the math 0. So this is a sort of thing. This was the sort of thing you did when you learned about elastic collisions. All right. Well, anyway, let's go and see what the problem is. And the problem comes back from the Maxwell equations. So one of the things that the Maxwell equations gave us was an electromagnetic wave. This just popped right straight out of the Maxwell equations. Oops. And the other thing that we got out of this was the speed of these electromagnetic waves. The speed of light was 1 over the square root of epsilon naught mu naught, which is just a shade under 3 times 10 to the 8 meters per second. And that also popped straight out of the Maxwell equations. Now, if you remember way back to thinking about Newton's first law of motion, one way that you can interpret Newton's first law of motion is to say that all inertial observers have to have the same laws of physics. And this sets up a little bit of a crisis for us here. So the Maxwell equations appear to be universal laws, although maybe they don't have to be. After all, when you do the Doppler effect for sound or something like that, you said, oh, we can only think about sound propagating in the medium it's propagating in, the air. So for the equations for sound, there's a special observer. And that observer is somebody who is stationary with respect to the air mass the sound wave is propagating in. So one possibility is that since all inertial observers have to have the same laws of physics, we've got this prediction that these electromagnetic waves are going at 3 times 10 to the 8 meters per second. So if the Maxwell equations have universal application, if they applied to absolutely everybody, then this requirement from Newton's first law that all inertial observers have the same law of physics, since these things just pop straight out of the Maxwell equations and are thus themselves laws of physics, everybody would have to agree that the speed of light is 3 times 10 to the 8 meters per second. The other possibility is that the Maxwell equations don't have universal application. Maybe it's like sound, where we can only apply them in the frame where the air is seen as stationary. Maybe there's some special observer who does all of the observing for the Maxwell equations. So it turned out, when people got to thinking about this pretty quick, they realized pretty quick that if there was a special observer, the sun had to be very close to being in the frame of that special observer. Now, the way that they were thinking about it at the time is because they were pushing this. They knew light was a wave, but they thought it was maybe more like a sound wave than it actually is. We now know that it's just fluctuations of electric and magnetic fields at points in space. They actually, at the time, were thinking about the possibility of it being more like a sound wave where something was being displaced or restored. They called this the ether, or the luminiferous ether, if you want to be fancy about it. But I'll make reference to this ether just because I think it's a little easier to think about. But absolutely everything that I have to say about that, we can also think in terms of just plain that the Maxwell equations are true, with the thought that the Maxwell equations are true only for a particular special observer. Now, it'll turn out they are true in general, but we need to think about this. So here's the deal. We know that the solar system has to be that the sun has to be almost at rest with respect to this ether wind, or our special observer. So the idea being, if it weren't, then the Maxwell equations being only true in a particular frame would give this sort of ether wind, if you will, if we hold to this older picture of light traveling through this medium called an ether. And so the rays of light coming off from the sun would kind of have to do a bit of a hook instead of traveling in a straight line. And so this would very strongly mess with our observations of when noon happens. When is the sun overhead? And we would not, depending where exactly we were in our orbit around the sun, we would be saying that days took well longer or well less than 24 hours between sunrises and sunsets and stuff like that. And it would just be a mess. So we were able to figure out that to within a few meters per second I think they got to even less than a meter per second. They figured out pretty quickly on the sun basically couldn't be moving with respect to this ether wind. But that did mean, that the Earth is not in the same frame. So in the direction of its orbit, it should always be seeing a headwind of this ether. And again, like I say, we don't have to actually think about the ether per se. We can go and do these velocity transformation exercises that I was mentioning before to boost into the hypothesized special frame for the Maxwell equations, do the calculations and boost out, and we'll get the same result. So there was an experiment done in Chicago by two physicists by the name of Michelson and Morley to test exactly this. Was there a special frame or not for the Maxwell equations? And their experiment was really ingenious. Now, because they didn't have lasers, they had used different technology and it made the experiment a lot bigger. The experiment was, I think, over 1 meter across. They had, in order to take care of vibrations, they had to build the whole thing on a giant granite slab that they floated on a pool of mercury. It was quite the ordeal. Nowadays, we can build one a lot easier by using a laser. So what you do is you shine laser light onto a partially silvered mirror. This is also known as a beam splitter. So the silvering is just the shiny stuff on the mirror. And there isn't enough of it to be able to bounce all the light. So some light will bounce off and some will pass through. So then what you do is some distance L above this beam axis here, you have a fully silvered mirror right here. So then if we follow the ray of light here, some of the light will bounce off of this. Now, some will pass through. We'll deal with that in a second. But for the light that bounces off, it'll go up to the mirror, bounce back off the mirror, and then about half the light will bounce back in toward the laser, which isn't so useful for us except when you're aligning the experiment to begin with. And then about half the light will pass on through. Then what you do is also a distance L downstream. You set up another mirror, like so. And so for the half of the light that didn't bounce but just passed straight through, it goes to this mirror and bounces back. And again, half of that light will pass through and just hit the laser beam. And the only thing is there again is it's useful for aligning the setup, but the other half of it will go down here. Now this will create an interference pattern, which we'll get into how to make these interference patterns a bit later. But suffice it to say, the waves of light here will interfere with each other onto a screen. And then we can look at that pattern. So usually you set it up so that, say, there's a bright spot in the middle of the pattern or something like that. Now, the next trick with this is that you align this axis to follow the direction that the Earth is traveling in the solar system. So by doing that, you would have our ether wind as a headwind onto our mirror. And again, if you prefer, you could talk about boosting into a hypothesized special frame. Doing the calculation, boosting back out, you'll get the same result. Anyway, the deal here is that with the head, because the light is traveling into the headwind, it should be going slower than the speed of light in the special frame going upwind and faster downwind. But that will work out to give us an average speed of light that's less than the speed of light in the hypothesized special frame. This is like those problems where, you think back in mechanics where they say, somebody traveled at, 50 kilometers an hour for 50, for 50 kilometers, and then traveled around and drove back the way they came at 80 kilometers an hour, or let's say 90 kilometers an hour. What's their average speed? It isn't 70. It's because on the way back they took disproportionately less time getting. They took not as they didn't save as much time going back as they wasted going up, and so the average speed winds up being more than the is less than just the numerical average of the two numbers. Now here with this leg, this is interesting because this is a crosswind. Here the speed of our light wave would be the speed of light in the special frame plus the squared plus the speed of the ether wind squared, take the square root, because this and this are at right angles. So this means that and they'll be the same both up and downstream. So the average speed here would be greater than the speed of light. So this means that this round trip of light over here should take more time if there is a special observer, and over here it should take less time. So if you've got all tuned up to make a particular pattern, now here comes the big trick. If you rotate the whole apparatus 90 degrees, you've now switched which leg is the more time leg and which leg is the less time leg. So there should be a difference in the interference pattern that you see as a result. And we'll get more into that later when we talk about light interference. But you should see a difference in the pattern. There was no difference in the pattern. The pattern did not shift at all. I think you can argue that this is, if not the most important null result in science, is one of the most important null results. Because there was no shift in the pattern, this meant that both of these observers, and then we can extend this out eventually to argue for all observers. Let's observers measure the same speed of light. They all agree that it goes at 3 times 10 to the 8 meters per second. It's the only way to keep this pattern from shifting. Now, that's not quite accurate. Some people did a calculation that showed that maybe that one particular spot in Chicago, when they did the experiment, was just where absolutely everything canceled perfectly, but replicating the experiment literally anywhere else on Earth took care of that concern. So, going back to what we're thinking about with the Maxwell equations, this popped straight out of the Maxwell equations. So we've now concluded that everybody measures that same thing. So this means that there is no special frame for the Maxwell equations. They are a law of physics that's true for everybody. So where did we go wrong? Well, the only place we can look back is thinking about this bit right here. Remember, we were saying this ether wind thing was the same difference as doing these kind of boost in and boost out calculations under the Galilean Transformation. So the idea was we were boosting to a hypothetical special frame and then boosting back out. And we found that there was no special frame. So this means that we're going to have to modify the Galilean transformations. You'll need modification. Now it's going to take us a few videos to do those modifications. And in the next video series, where we will start picking up on this, is some thought experiments due to Albert Einstein. So catch you over there.